Good morning. Let's talk about this large number that you see on the screen. And let's ask ourselves, is this a prime number? And more importantly, how long would we take to find the answer? This number reads 9 decillion, 999 each of a nonillion, octillion, septillion, sextillion, quintillion, quadrillion, trillion, billion, million, and thousand, and 991. That was long. I confess, I browsed the web to get those words. In short, it's 33 nines followed by a 1. Now, is this number a prime? Let's say you have a pen and paper for you to work it out. If you were to do it by hand, how many blank pages of a notebook do you think you would require to find the answer? Let's make it a little easier. Say you can use this pocket calculator that can add, subtract, multiply, and divide for you. Now, how long would you take? Let's just get started and try out. How would you approach the problem? The most basic way is to try finding a proper divisor less than the square root of that number. If there is none, we can then declare that the number is prime. 2 doesn't divide it, the number is odd. 3 doesn't divide it, 5 doesn't divide it. 7 looks promising, but when you use some modular arithmetic tricks or scribble with a pencil and paper, you'd find that 7 doesn't divide either. A quick look at the sum of alternating digits shows that 11 also doesn't divide. By the time you come up to 13, this surely appears a very bad and hopeless idea to you, even if it didn't at the beginning, because you just don't know if or when some number would cleanly divide a large number. And to confirm that it is a prime, we'll have to verify dividing it by all prime numbers till 100 quadrillion, that is 1 followed by 17 zeros. This doesn't feel feasible at all, and you would actually need a way lot more paper than what you see in that picture, even if you had enough time for it. And even if you can check division by one prime number every second, you will need more than 100 million years for this. Calculator isn't that useful then. Even if you implement and run this basic idea as a program in your laptop, that still takes a lot of time because of the largeness of the number in hand. A lot of time. You could go for more sophisticated algorithms for your program, but this video is not about that. While this might seem directionless at this point, let me tell you this. A high school student can solve it way quicker than any of these methods. Yes, a high school student with elementary knowledge of algebra can tell the answer within a minute. This might be a good time to maybe pause the video for a few seconds and ask that inner high school student in you to help you out here. If you took some time and solved it, that's great. You have a very keen eye for numbers. For others who are here to enjoy the show, this algebraic identity is what the high school student would need to know to answer our question. A squared minus b squared equals a plus b into a minus b. Now the solution idea becomes obvious, doesn't it? Let's look at our giant once again. 33 nines followed by a 1. The key observation here is that our number can be written as 10 to the power 34 minus 9, which is 10 to the power 17 squared minus 3 squared, which by the algebraic identity equals 10 raised to the power 17 plus 3 into 10 raised to the power 17 minus 3. That is the product of these two numbers. So wow, that number is indeed composite. And you were doomed if you had persisted with our earlier approach of trying to find a divisor moving upwards. The reason being, both these numbers are primes themselves, which means you would find the divisor and thus the answer to the question only when you finally reach up to the primes close to 10 to the 17. In fact, it would be the last number on that list. I am glad we summoned the high school student to us. Let's be careful here. The kid still wouldn't know how much time he has saved. He doesn't know if those are the only two divisors. He wouldn't know if the two factors he found are primes. But that doesn't matter. He still sufficiently answers the question of whether our giant number is prime or not. You should note here that our big guy is not the only special number around that can be expressed as a difference of two squared numbers. Let's look at 1, 2, 3, 4, 5, 6, 7. This can be represented as the difference of two numbers, which happen to be squares, thus giving us a factorization of 9721 times 127. But it's not possible for a human to observe or find out such structures in 1, 2, 3, 4, 5, 6, 7 and express it as a difference of two squares like this. Whereas Our number, which is aesthetically pleasing with a lot of 9s and a single 1 at the end, is also a bit more revealing of what structure we want to observe out of it. It is very much possible for a normal person to quickly see that the number is the difference between 10 to the 34 and 9. Our giant has a smaller brother who fits our purpose, 9991. When we question if 9991 is prime or composite, the number being not that big, it's a little more tempting to try out by hand with brute force. But that would be a poor choice, because 9991 is 103 times 97, both being primes themselves and both being very close to the square root of the original number, making life hard. Anyway, this was a nice piece of maths that I came across in my childhood, so you don't really need a computer or a calculator or even a pen and paper to answer that question. All you need is a few seconds of a high school student's mind. It's so beautiful that a seemingly hopeless prime checking problem takes a hint from an algebraic identity. Thanks for watching. Let me know what you think in the comments. Have a nice day.